I'm going to talk about the oxidation state of sulfur in apatites, which is a phosphate mineral that's found in a variety of rocks from the moon, from Earth, and from Mars. On the title slide here, I'm showing you a backscatter electron image of an Apollo rock sample recovered from the moon by the Apollo astronauts on the 12th mission. And the apatites are these kind of medium gray, hexagonal shaped grains that you're looking at in this diagram. So we're gonna talk about how we measure the oxidation state of sulfur in these minerals and why it's interesting or important. And I'm gonna start, here we go, with kind of the broadest motivation of what it is that I do as a geologist, as an igneous petrologist or a geochemist. And broadly speaking, I'm interested in oxygen in the rocky planets and how much there is, its activity, and then distribution through the layers of planets as they differentiate into metallic cores and silicate mantles and crusts, and in some cases, like on Earth, a water-rich and oxygen-rich exterior. And I just wanted to talk about the behavior of oxygen in solid Earth or solar system materials because it behaves a little bit differently from the other elements that we're used to thinking of. And I'll begin with a list of the 8 most abundant elements that make up the Earth. If we consider the Earth as one rock and we were to measure its major element composition, this is approximately what it would look like. And you'll notice that oxygen is on this list, and it's really high on this list. And that's an important point, is that there is an enormous amount of oxygen bound in the solid Earth, similarly for the moon and for Mars, Mercury, Venus, and the asteroid belt. It's got a lot of oxygen in it. But unlike the other elements on this list, most of the oxygen in the solid Earth is tied up by being bound with oxidized cations, right? So we are 32% by weight of iron, but a lot of that exists as iron oxides, as ferrous and ferric iron. And so a lot of the oxygen that's bound in the solid Earth is hard bound to those oxidized cations and is not active or reactive to promote reduction oxidation chemistry. This is really different than the case of the atmosphere, where there is much less oxygen by mass present in Earth's atmosphere than there is in the solid Earth. But what is there exists as the dioxygen molecule, which is very reactive and will readily take metallic or reduced versions of the other cations and oxidize them. For instance, metallic iron in steel will be oxidized to ferrous iron and then ferric to rust it, for instance. So there's a lot of oxygen bound in the solid Earth, but what's there is not very reactive. There is not a lot of oxygen in the atmosphere, but what is there is very reactive. And what I'm mostly going to talk about today is the activity, the reactivity, the availability of oxygen in these various layers. And we're going to keep track of it by measuring or by talking about the amount of that very active, that dioxygen molecule, that available oxygen to promote reduction oxidation chemistry. And so, for instance, we know that the partial pressure of oxygen at sea level is something like 0.2 atmosphere. And so the log of that number is minus 0.6, so that Earth's atmosphere falls to the hard right on a diagram like I'm showing you here. By comparison, basalts that erupt to the surface of Earth have about 7 orders of magnitude less available oxygen than Earth's atmosphere. So again, this rock is going to be 30 or 40% by weight of oxygen, but there's going to be a vanishingly small amount of that that is not tied up by balancing titanium 4+, aluminum 4+, silica 4+ in the rock itself. Basalts that are up to the surface of the moon have 4 orders of magnitude even lower. They have much lower log PO2s, and they have available oxygen similar to that recorded by the equilibrium between metallic iron and ferrous iron oxide, which is called wustite. So that the moon, we think, is something on the order of 11 orders of magnitude lower in this availability of oxygen parameter that we're going to think about. Now, so that we don't have to keep track of very small numbers throughout the course of today's talk, I'm going to use this equilibrium between metallic iron and wustite as a reference. It's called the iron-wustite oxygen buffer. And I'm going to reference values of the log PO2, or the availability of oxygen, relative to this, such that if I were to say, talk about the availability of oxygen in terrestrial basalts, which is 4 orders of magnitude higher on this scale, I would call it iron wustite plus 4. And then Earth's atmosphere being 11 orders of magnitude higher in this parameter would be iron wustite plus 11. It's important when I'm talking about these values as we move forward in today's talk to always remember that this is a log scale, and so differences are going to be at the order of magnitude. Okay, so if we look at how the availability of oxygen varies in the inner solar system, this is the view that we get. We see that the solid Earth spans this enormous range in the availability of oxygen, and that it has this kind of remarkable parameter that it has an atmospheric Earth's surface that has this very high availability of oxygen. I've put Mercury and Venus as semi-transparent on this diagram, and that's because constraints for these planets are relatively uncertain, which in large part is due to a lack of material that we have on this planet from those planets to measure. But we've got a decent amount of material in the meteorite collections from Mars, and we've got, of course, the Apollo rocks from the moon. And the variety that we see in the activity of oxygen in the solid Earth and Earth's atmosphere, we understand fairly well. This is, I spend a lot of time thinking in this community, and last week you heard from Megan Holycross, trying to understand this distribution much better. But what we see is that a lot of the large spread that rocks on Earth are pulled to these very high oxygen activity values because of the presence of life at Earth's surface and the production of oxygen in our atmosphere that serves to oxidize rocks. And then plate tectonics will physically mix material that's been exposed to this very active oxygen exterior back into the interior of the Earth to create more oxidized rocks. When we look at Mars, we see that there's a similar, pretty impressively wide range in the activity of oxygen from the Martian meteorite collection, which are basaltic and cumulate rocks from Earth's crust. But Mars is really different from Earth. There's no significant body of evidence that suggests that there's been plate tectonic activity on Mars, and so it becomes a good question to answer what kind of volcanological processes or crustal processes are happening on Mars that creates this widespread in the activity of oxygen in rocks on Mars. I'm going to do that, though, by first taking a look at some rocks from the moon, because this is kind of like the journey that I took to thinking about the activity of oxygen on Mars. That a colleague brought to me a mineralogical puzzle about some work that he had on lunar rocks, and we ended up using synchrotron spectroscopy to solve the puzzle. So I'll tell you about that today. The puzzle is rooted in our understanding of the formation of the moon and the implications for the highly volatile elements. And so that's hydrogen, sulfur, carbon, the very volatile elements. And the leading hypothesis for the formation of the moon is that it formed through giant impact. And so that in the early solar system, we had the proto-Earth was impacted by a Mars-sized body, and that the collision and the aftermath eventually led to the formation of the Earth-Moon system. And I have a quote here from Eric Howry describing the early solar system as a chaotic place at the time that the moon formed, crowded with all manner of asteroids and embryos in a constant state of collision. And in the early stages of planetary formation, these collisions, known as giant impacts, were violent enough to result in wholesale melting of colliding bodies. And that statement comes or is supported by work from Robin Canup, who simulates what these large planetary collisions would look like. And you're seeing an example of the giant impact that could have formed the moon. And the color scale on this figure is temperature in degrees Kelvin. And so it's demonstrating to you that in the immediate aftermath of the moon forming collision, the moon, both bodies would have been partially or fully melted. And that these very high temperatures are expected to have driven off, boiled off the highly volatile elements that might have been bound in those planets at the time of their formation, including hydrogen and sulfur and carbon. And that when these bodies were cooling, the Earth with a larger mass would have reaccreted some higher proportion of these highly volatile elements, but the moon would not have been. And so we expect that a major result of the giant impact would be that the moon is very, very dry. There is very low water, very low carbon, very low sulfur. That is the expectation of giant impact theory, which is surprising then in the last decade when Eric Howry, together with Alberto Sol, started measuring on secondary ion mass spectrometers with very low detection limits, very precisely the water concentration present in the volcanic rocks, the glass beads that erupted to the surface of the moon. And to their surprise, found that the glass beads contains tens of ppm of water dissolved in them. And that these higher pressure glass phases, what I'm calling melt inclusions here, contain hundreds of ppm water dissolved in them. This observation extends to the apatite record, which is a phosphate mineral that can incorporate water into its mineral structure, where Francis McCubbin and Jeremy Boyce and Jim Greenwood at the same time were finding that there are hundreds to thousands of ppm water bound in apatites from the lunar rocks. And when you start approaching, when you get up to 1,000 ppm and higher, you start approaching water concentrations like we expect on Earth. And so this observation has been huge and reinvigorated a lot of interest in the giant impact theory for how the moon formed, and seems to require modification, at least, of how that process unfolded in order to allow the moon to retain water concentrations, at least in some portions of the crust like this. The observation extends to sulfur. If you look at the sulfur concentration of these glass beads, what I'm calling matrix glass here, and those higher pressure glass phases, melt inclusions, we find that there are hundreds of ppm sulfur dissolved in lunar magmas at their time of eruption. And this is the mineralogical puzzle. The observation extends to apatite. There are hundreds of ppm sulfur dissolved in apatites in lunar rocks. Why is this a puzzle? This is a puzzle because apatite is a phosphate mineral. I'm showing you the mineral formula here. And based off of our study of rocks from Earth, we expect sulfur to partition into apatite as the sulfate anionic group, sulfur 6+, in a charged couple substitution either with sodium or the silica tetrahedron. This is an issue for lunar rocks in particular because, like I showed you earlier, in these introductory slides, the activity of oxygen recorded by lunar rocks is very, very low. Here I'm showing you, this is, I'm calling it now FO2, the fugacity of oxygen. Here's that value set by the iron wüstite oxygen buffer that we think is relevant for the lunar crust, and we're extending to more oxidized values to the right. I'm also showing on the y-axis the oxidation state of sulfur in silicate magmas, right? It can be dissolved as either sulfur 2- or sulfur 6+, and I'm representing that as the proportion of 6+ to total sulfur. And the circles that I'm showing you are a variety of experiments where they have fixed their FO2, so they know their value on the x-axis, and then through sulfur Zanes measurements of their quenched experiments, they determine what is the oxidation state of sulfur in those glasses, so that now we have a clear expectation of how the oxidation state of sulfur in magmas should change as a function of the activity of oxygen of that magma. And what you'll notice is that the activity of oxygen recorded by the bulk mineralogy of lunar rocks, which is pretty well understood, is 4 or 5 orders of magnitude too low to stabilize sulfur 6+ in the magma. So if you can't stabilize sulfur 6+ in the magma, there is no sulfate anionic group available to partition it into apatite in the first place. So it was very surprising and very difficult to explain why there are hundreds of ppm sulfur bound in apatites from lunar rocks. There are 2 options. The first is that those lunar apatites and the melts from which they grow contain sulfur 2-. And Brian Konecki has done some great work creating these apatites experimentally. So in similar ways that these groups are creating silicate melts Brian will grow apatites in his silicate melts and has demonstrated through Sulfur Zane's work that these experimental apatites can dissolve sulfur 2- into their structure, but we haven't seen it in the natural rock record. The second option is that they contain sulfur 6+, which would require some mechanism to oxidize those late stage magmas. If the bulk rock mineralogy is telling you that they're down here at iron wustite, then there's got to be some last minute during eruption, during cooling on the lunar surface that increases the activity of oxygen by several orders of magnitude in order to stabilize sulfur 6+ to partition it into the apatite structure. I'm going to stop there for questions. That is the premise. So what we need to do is understand what is the oxidation state of sulfur in these apatites from the Apollo rocks. And if people had questions about my path or why we're doing this, I'm happy to answer them.
I'll ask a question while we wait to see if anyone remember to type your questions into the chat. I didn't quite follow the very last step about the melt containing the sulfur 6+.
Sure. So if the apatites grow from the melts, from the magmas themselves, and in order for sulfur 6+ to be present in the apatite, in the substitution mechanisms that we're familiar with, we need to have sulfate in the melt in order for it to partition and be incorporated into the apatite like we expect it to.
Okay, so the mystery here is figuring out how there could be so much sulfur 6+ in the final apatite.
Correct. It's not all that unusual to find apatites with hundreds to thousands of ppm sulfur on Earth, and that's because Earth has much higher oxygen activities in its solid material, so that there's plenty of sulfate around. It's common for apatite-bearing igneous rocks to be up here at a value of iron wustite +5, iron wustite +6. The melt has 1,000 ppm sulfur in it. It's all present as sulfate, so you put it in the apatite structure according to these relationships.
Okay, got it. Neil, you have a question? Neil Hyatt?
Thanks, Jerry. Can you hear me okay?
Yes.
So Maryjo, fascinating talk. I'm excited and anticipating how it's going to pan out. My question for now is, what's the sulfur solubility limit in like the glassy phase as sulfate and S2-, and how close do you think you are to that with these sort of hundreds of ppm concentrations?
Yeah, that's a great question. So there are two main controls on the solubility of sulfur in silicate magmas. The first is its major element composition. So the difference between these two groups of experiments that I'm showing you here in gray and in black are the major element compositions of the melts that they're studying. These melts over here are typical of like Earth basalts, and what we think is important is the concentration of iron and calcium, where if you decrease your iron concentration and increase your calcium concentration, which is what this study is doing, you're able to stabilize sulfate at lower FO2. And in general, silicate melts can dissolve more sulfate than they can sulfide before coming up with a new phase that it wants to hold the sulfur in. So major element composition is important. If you're down here in the sulfide only range, your total iron concentration becomes important, whereas the iron concentration of the silicate liquid increases, the solubility of sulfur 2- also increases because there's a relationship between iron and sulfur in the mixture itself. And then the second important constraint is pressure, because sulfur is a very volatile element that when you take a basaltic liquid or any other major element liquid from, say, 100 bar total pressure to 1 bar total pressure, the solubility of sulfur, whether it's 2- or 6+ or whatever its major element composition is going to go down. So at 1 bar, you're going to have maybe 10 ppm sulfur dissolved in that liquid. But at 100 bar, you can have 1,000 ppm sulfur if it's reduced, and maybe a weight % if it's oxidized.
Okay, that's really kind of interesting. I've got a bunch more questions, but I'll wait to see if you answer them in your talk. Thanks a lot.
Okay. It's also the last thing there, important to remember that the lunar rocks are erupting into the vacuum of space. so not to the pressure of Earth's atmosphere. And so we really expect those very last liquids to have, 100 ppm or lower sulfur.
All right, Matthew Marcus, you had a question?
Just out of curiosity, where does the sulfide go in the apatite structure? Does it go in the anion site?
Yeah, I'm going to get to that later. But that's what we think. Yeah, it'll
And I guess you'll
in there for fluorine or chlorine or hydroxyl.
I guess you'll also mention what kind of Zane's references you use, because most sulfides that you would just pick up, like say iron sulfides or semiconductors, so they're electronically very different from sulfide and apatite.
Yep. Yeah, the choice of the reduced end member is important. The spectral
Okay.
will change pretty dramatically.
Colin, you had a question?
There it is. I was wondering, Maryjo, are the sulfur concentrations measured in apatites correlated with hydrogen isotopes in the same apatites, or is that known yet?
That's not known yet. That's a really good question, and
Okay.
Could be, yeah.
Okay.
Yep.
Yeah, I mean, it'd be another clue, I guess, in this puzzle.
Stoichiometrically, right? If there is sulfur 2- in the apatites, then stoichiometrically, the abundance of sulfur 2-, fluorine, chlorine, and hydroxyl should sum to 1. And there's some evidence actually in the Martian rocks that we've not measured sulfur 2- in those rocks, but they've got a stoichiometric problem with fluorine, chlorine, and hydroxyl. That, to me,
I think you can get oxygen also, right? Like apatite. But this would be for isotopes specifically of hydrogen.
Yeah, to my knowledge, I don't know that people have combined those two data sets. Okay. I think maybe those two data sets exist in the appendices of maybe Jeremy Boyce or Jim Greenwood's work.
Okay.
But no one's looked at that explicitly.
Okay, thank you.
All right, a last question for the moment is, what's the time scale, such as kinetic parameters, for sulfate to dissociate under vacuum?
Great question, and I don't know the answer.
Okay, that's fine. All right, you should continue. Thank you.
Great. So, right, these are our two options to explain hundreds of ppm sulfur in lunar apatites. We're going to use sulfur Zanes to solve this problem in a actually pretty straightforward way. All the work that I'm going to show you today is done at the Advanced Photon Source with the Jesse Cars group, and from this point on in the talk, everything that I say is said with special thanks to Tony Lanzarotti and Matt Neuville for help with the setup. And I've put some parameters here of our measurements on the slide because this seems like a group that would be interested. And so I'll start here. So we're at 13 IDE, sector 13. At the IDE hutch. We're doing the sulfur measurements obviously in a helium atmosphere. Sorry that the picture is a setup for iron, but because it's done in a helium atmosphere, there's like a whole contraption that doesn't make for as nice a picture, but rest assured, they are done in a helium atmosphere. We're using a 111 mono and a silicon drift diode array detector. Our beam is nominally focused, although we've played around a little bit with this, defocusing to as much as 10 by 10 microns in some of these measurements. And it seems like we can get away with a 2 by 2 micron focused beam. But we do attenuate the photon beam coming down the line to be on the order of like 10 to the 10 photons per second. And this is because we're generally sensitive to the possibility that we're going to do electronic damage to our samples, in particular because I'm going to be measuring the apatites, which is a hydrous phase, and so may be delicate. But at the same time, like in a single session, I'll measure a variety of phases in these thin sections, including glass. And even though I expect, again, these glasses to have very low volatile concentrations, because ultimately the rocks are erupted to the vacuum of space, we're just sensitive to the problem. So we attenuate the beam because we can still get decent signal to noise at 10 to the 10 photons per second. The spectra today, I'll show you sulfur Zanes in fluorescent mode between a little bit over 2400 EV to a little bit over 2500 EV. And we also combine these measurements with XRF maps for major element chemistry. And And this is because we want to really precisely correlate our Zane's analysis spot to what the beam is seeing, the beam position at the time. And again, that helium atmosphere just a little bit tugs on the geometry of the equipment as we're kind of moving around our slide. And every micron counts for some of these phases because the apatites are small. Here's that backscatter image from the title slide again, and the scale bar is 100 microns. These are particularly large apatites. These, again, they're the medium gray hexagons, particularly large. And if you look very closely, it'll be more obvious later when I zoom in, but in backscatter anyways, these are showing evidence for zonation. And so we really, really want to know precisely where our analytical volume is. So we do this XRF mapping and then pair specifically pixels from the XRF map to beam positions to switch to the Zane's measurements. And my co-author, Jeremy Boyce, had originally tried to do this using a conventional microprobe at Caltech, and he had results suggesting that there was all of this oxidized sulfur in these lunar rocks he was really excited about, but I think I'll show you with the Zane's measurements, it became really clear that that was potentially beam damage at on the electron microprobe. And it seems to have both moved the oxidation state in a reducing and an oxidizing direction. And so I think it is becoming really clear that we should stay away from conventional microprobe measurements for stuff like this. Whether we're doing beam damage at 13 IDE with our setup like I described here, we're talking about it, but it appears, if it's happening, it appears unidirectional, which is to take some proportion of sulfur 6+ and reduce it to sulfur 4+. And it does not go to completion. So this is our setup. And here's what 2 of these spectra look like. So someone's asking me what I'm using is end member spectra. And for the reduced sulfur end, we'll use a troilite spectra because it matches peak shape really well when we look at the glasses and the apatites that contain only sulfur 2-. It fits the peak shapes really well. And then I'm also showing you, a spectra of an apatite from Earth called Durango apatite. This is a common apatite used as a standard. It's from a volcano in Mexico. And I've marked the positions of the K-alpha features for sulfur 6+, really sharp, really narrow, and really reliably showing up at like 2482 EV. And the sulfur 2- peak shapes, which can vary, as I think it was Matthew pointed out, depending on what your associated cation is, but troilite seems to do a fine job. So we're looking for peak shapes at these energies for sulfur 2-. You'll notice here on either side of the sulfur 6+ peak for the Durango apatite that there are 2 peaks on either side. This is the peak position for sulfur 4+. It's where we expect it to show up. And the conversation about the possible extent of beam damage is whether this is real and in the apatite or whether that is a product of beam damage in the 5 minutes or so it takes for us to collect counts up to the sulfate peak. And so that remains unclear, but for the kind of level at which we're trying to understand what the range of sulfur oxidation states in these apatites are, it's not going to be a major problem yet. And so I think I'll stop here again, because now I'm going to stop talking about how we actually collect the measurements. I'm going to show you the data from here on out. So if anyone has questions here, I can try my best to answer them, but maybe Matt can help me.
Yeah, a few questions. So you're in fluorescence mode here, yes?
Yeah.
And would it be possible to increase your detector solid angle, or were you already kind of as close as you could get with your solid state detector?
That's a great question for Matt.
Thanks. This is about as good as we can do right now. Actually, so we're in the process of commissioning a larger detector, but we don't know that that will actually be a bigger solid angle and total counts for sulfur, especially.
I see. That of course would have a high bearing on beam damage question, just being able to collect the fluorescence faster. A related question, and I'm sure this is difficult presently, but am I right? It would be beneficial if the samples could be cold when you were measuring them to try to decrease beam damage, or is that much more of an organic issue, an issue with organics, and it won't help with the inorganics?
So well, I would let Maryjo answer this, but I'll take over. Our experience with photo reduction in mineral phases is that the small amount of cold work we've done has not helped significantly. We think
Has
that
not, sorry, say again louder?
has not helped.
I see.
In fact, in cases, it's made it worse, possibly. It might be that you have to cool to like 10 Kelvin in order for that to actually be effective. And then cold and in a helium bag for sulfur to get the sulfur x-rays out is another level of complication that we haven't even attempted doing.
I see, I see. I'll note Liz Cottrell mentioned that iron zanes done cryogenic is worse for beam damage.
Right.
All right. Martin Stennett, you had a question. Do you have a mic, or shall I ask your question? All right. While he's thinking, I'll move to Matthew Marcus. You had a question?
Come on, unmute. I was wondering, you mentioned photooxidation in EPMA, and I was kind of wondering where the oxygen would come from to do the oxidation, since it's in vacuum.
I don't know. I just know, I am referencing here just the empirical observation that Jeremy came to me with data that looked more oxidized than anything that I've been able to collect at 13 IDE in the same thin sections. Yeah, that's the observation. There's another observation on experimental silicate glasses. This is work from Pedro Hugo at ESRF, where he notices something similar in hydrosilicate glasses, where he does peak shift on conventional microprobe and then sulfur zanes at, I want to forget the number of the line at ESRF, but shows that the historical conventional EPMA sulfur oxidation state work is canted. The 6+2- relationship with the activity of oxygen is canted off of the true slope that he can return from Zane spectroscopy, suggesting that the oxidized stuff gets reduced and the reduced stuff gets oxidized. Mechanistically, I don't know how that's happening. Just an empirical observation.
Okay.
Yeah. So Matthew, I think a lot of the oxidation or photo reduction we see is actually hydrolysis causing oxidation. So not necessarily direct oxidation of the cation you're trying to excite, but the creation of free radicals. And there is some available hydroxyls around.
Okay, so the oxygen comes from the water.
Yeah.
All right, moving on. Martin, you had a question?
Hi, yes. Can you hear me?
Yes.
It was just a question about the beam damage, the potential beam damage you mentioned. Have you or anybody else tried to do any studies trying to look at that? Maybe repeated scans on the same spot to see if those features change in size or magnitude?
Yeah, this is where the statement does not go to completion comes from, because for certain within the parameters of our within our collection parameters, we can go through and collect this one spectra, and it takes something like 10 minutes, 11 minutes, depending on just some details about dwell time, so that we're in this region by about 5 or 6 minutes in, and we can just sit there and count for long periods of time. And when it's on an apatite, the structure of the spectra doesn't change on the course of tens of minutes to hours, which is what I mean when I say it does not appear to go to completion. So that if it is beam damage, it seems to be created within 5 minutes and then does not evolve past that point. This is different from silicate glasses. I've done some sulfur work in glasses from Hawaii, where I sit there again on the order of tens of minutes at the same spot, and I see continual decrease of the sulfate peak and growth of the appearance and growth of a sulfite peak at the same time, and that does not appear to reach a steady state until maybe 2 hours or more into the analysis. If we, I don't know, we could try doing like fast scans, or we could park it at the sulfite peak and just count and see if we see a change in counts through time. And we've not done that yet.
What's your beam spot size, Maryjo, roughly?
2 by 2 to 10 by 10. We messed around
Okay.
with that a little bit, and it didn't seem to make a big difference at 10 to the 10 photons per second.
Okay, so this is very much a focused beam problem. I get it.
Yeah.
All right.
Oh, for sure. Yeah.
Yeah,
The way we solve this problem in silicate classes is, number one, to attenuate the photon beam, but also defocus the spot. So we're doing 25 by 25 or 50 by 50 micron spots in hydrous glasses from Earth for iron and sulfur, and then the problem goes away.
I see. I see. Liz Cottrell, you had a question? You wanted to bring up TESs? Okay. Anyway, Liz was bringing up in the chat whether you had considered trying to use the, trying to work at the TES beamline. The acronym is used too many times in this talk series. Whether you considered using the TES beamline at NSLS2? Yeah,
for sure. I was tuning in, what was that now, a couple weeks ago, to Paul Northrup's talk, and it sounds really interesting. And so APS is going to shut down eventually, so I'll need to go somewhere.
Yes, for the upgrade. Yeah.
Yeah, exactly.
All right. Very good. Then you should continue, please.
Okay, thanks for
All right, sorry, I was having a technical issue there. Can you repeat?
Yes. Hi, Liz.
Hi. You were talking about the tender X-ray line?
Yeah.
Yeah, it's on my radar.
Okay, glad cleared that up.
Sorry, I saw TES and thought transition edge sensor, and I think there's good reasons to want to use that here to try to do RICS more efficiently, but that's a topic.
I don't know what that is.
A topic for a different day. There were a couple of lectures in this series about that kind of solid state detector, and
cool.
They do exist at NSLS2.
Well, I will go back to the YouTube channel and learn something.
All right, you should continue, and thank you for taking all the questions.
No problem. Okay, so here's the answer. We're going to start. I don't know why this is the case, but Apollo 11 rocks, I'll start with the prefix 10. So this is an Apollo 11 rock. Rock number 44, it's a high titanium basalt, and it contains a variety of phases that to an igneous petrologist signals almost immediately a very low activity of oxygen during crystallization, about an order of magnitude lower than the iron wolfstite oxygen buffer. And things that stand out here are the presence of iron metal itself and an equilibrium between phaolite and silica and the presence of ulvospinel. Here's a backscatter image of apatite grain. It is in equilibrium with this, or it's touching, in contact with this kind of complicated texture down here to the right, where we see the presence of phaolite and silica. And so here is an apatite in this Apollo 11 rock that knows about the very low FO2 activity of oxygen during crystallization of iron wolfstite -1. The apatite itself is clean, so there's not a lot of cracks or fractures or anything like that. Here's one of our XRF images taken at 13 IDE. So blue is sodium, green is phosphorus, and red is sulfur. So you can see the apatite shows up as nice and bright green, and that there is significant amount of sulfur in this oxide blade that's coming in behind the apatite. And here are our sulfur-Zane spectra of the 4 points that I'm showing you on the images, and you see the very clear evidence of sulfur 2- and no evidence for sulfur 6+, which solves that mineralogical puzzle, which is that lunar apatites contain exclusively sulfur 2-. So they are able to contain hundreds of ppm sulfur by virtue of incorporation of sulfide into the apatite structure at the very low FO2s expected for the crystallization of these rocks. So that was really exciting because this is it's a first, which is always fun. So this is a first demonstration in the natural rock record of sulfide only bearing apatites, and confirms hypotheses that put forth by Brian Konecki and others working around him that this is possible. And so that's really great to learn that they're on the right track, and that those experiments are going to be available to help us develop an oxybarometer. And again, it solves that problem. We don't have to worry too much about how much more oxidized might portions of the moon be. It's not required that they be very oxidized at all. We can look at a different rock. Here's an Apollo 12 rock. By this point, the prefix 12 lines up with the mission numbers. Rock number 39, it's a low titanium basalt, so it's a little bit of a different major element chemistry. Again, it contains a variety of phases that indicate very low activities of oxygen during crystallization, including ilmenite, the lack of ferric iron oxides in the rock, again, the presence of iron metal blebs. And I really, really love this particular section. This is a zoom in shot of the photo I've been showing you on the title slide and on the methods. Scale bar down here is 50 microns. And the first reason that I really like this image is because these apatites are so clearly igneous that an igneous petrologist looks at this and knows that these apatites were crystallized from a silicate liquid, including that they've got really beautiful hexagonal shapes. And so they're euhedral. They're the shape that we expect apatite to be when it's crystallizing. It also, because you see the nice hexagonal crystal forms here, if I compare that to the rectangular crystal form that you see in the Apollo 11 rock, what we've done is now captured apatites in the thin section that are oriented according to its crystallographic axis in a different direction than in the Apollo 11 rock, so that we can kind of indirectly test the extent to which anisotropic measurements might be troubling us. And the other reason I really like this, there's a sulfide bleb in this image, this really bright thing over here to the right, and it's got a rounded contact with the glass, demonstrating that the sulfide and the glass were liquid at the time that the apatites were crystallizing, and that the liquid, the apatites are embayed by the liquid itself, which really clearly ties texturally an igneous background for these, an igneous origin for these apatites, which is really great. We do the same thing. Here's our XRF map. Again, it's a sodium, phosphorus, sulfur map so that the apatites are showing up nice and green, and we can plot our points very precisely and measure the glass and the apatite and the sulfides in this particular thin section. I'll start at the bottom here. For one, this sulfide that we're measuring has these sort of low, the sulfur 2- peaks that where we expect them to be, but it's got an even lower energy peak down here, which on this particular image I'm marking as sulfur 2-, although work from Adam Simon's group thinks that this might be sulfur 1-, perhaps, based on some measurements of rocks from a mine in New York. But it becomes a useful tool for this work because we can demonstrate that we're not accidentally including portions of the sulfide in our analytical volume when we measure the apatites. The penetration depth for sulfur at these X-ray energies is very low, but I find that this crops up as a question that people have, especially when you see textures like this of the sulfide kind of layering very closely to the apatites. Because the apatite measurements lack that low sulfur peak, we can say pretty confidently that this is not a problem that we're having. We also measure the glass in both of these locations, and we find that the glass contains only sulfur 2-, and that really helps us support this idea that the sulfur that's present in these apatites is only sulfur 2-, because the liquid in which it's in contact with the evidence that they were all a liquid and the apatite was growing from the liquid at the same time, tells us that there's no sulfate available to partition into those apatites at the time of their growth. We have a variety of measurements, again, with sulfur 2- features and a lack or very, very small sulfur 6+ features in them, supporting, again, that these apatites contain sulfur 2-. And then the puzzle, because every once in a while we get a spectra on the apatite that looks like this. We know we're on the apatite because we do these careful XRF maps, and we sometimes, occasionally get very strong sulfur 6+ absorption features. And this is the new mineralogical puzzle. Okay, so I'm going to turn these spectra into sulfur 6+ to total sulfur ratios. This is nothing fancy in this particular case. I'm just taking the sulfide only and sulfate only spectra and doing linear combinations to create synthetic spectra and doing an error minimization problem with the unknowns. And then I'm saying the proportion of each of those spectra that I had to mix together to create a synthetic that best matched my unknowns is the sulfur 6+ to total sulfur ratio for these apatites. So now I can show you what the bulk of measurements across this thin section looks like. Here's the sulfur 6+ to total sulfur ratio, where this is primarily tracking the intensity of that sulfate peak. You can see that the vast majority of these measurements fall at a value down here between like 0 and 3%. And I'm calling anything below 3% effectively 0 because some of these have very low sulfur concentrations, and so the spectra are really noisy. And so anything in this light gray region, I think I would not confidently tell you that there was significant sulfate absorption features in those spectra. Both of the glass points are down here at 0, and then you can see that there are, hang on, all your faces are kind of over the chart. There are 4 or 5 analyses here on apatites that, I know I should have done that, there we go, that have really significant sulfate absorption features in them. And what I'm also showing you is the position. You can see that this thin section has some fractures and some pits running across it. And every time that we find these really intense sulfate absorption features, we are close to an area that's like pitted or fractured in the thin section. And so we conclude again that the lunar apatites contain sulfur 2-, but that there are sulfur 6+ absorption features in some of these spectra. We think it's a secondary sulfur 6+ bearing phase, so it's not sulfur 6+ dissolved in the apatite, and that it appears to be associated with pits and cracks in the thin section. And now the question to answer is whether that has lunar or terrestrial origin. So whether this is a sulfur 6+ bearing phase precipitated in the fractures of these rocks during some kind of impact event on the moon, or a hydrothermal event happening at emplacement or after, or if it is a simple consequence of bringing these rocks back to Earth. And these particular rocks, they're curated, but not in any particularly special environment since their return in the 60s and 70s. And so it might be that they've just been thin sections that have been kicking around in everybody's labs for the last handful of decades, and that we've created some sulfur oxidation from these otherwise very reduced rocks. Okay, I'll come back to that thought in a second. But now we are able to, this is similar to a plot that I showed you at the beginning, but important difference in that now we can put the sulfur 6+ to total sulfate of apatite on the y-axis here, not of silicate melts, and plot it versus the activity of oxygen in a variety of these rocks, where we find that the moon has this very low activity of oxygen and the apatites contain sulfur 2-. We know on Earth that terrestrial apatites are formed at pretty oxidizing conditions and contain only sulfur 6+, like for instance the Durango apatite that I showed you at the beginning. And then here are some of Brian Konecki's experiments where he's setting and controlling his FO2 and growing apatites that appear to have mixed sulfur speciation. And what you see forming maybe is that characteristic sigmoidal form of the relationship between oxidation state of sulfur and oxygen activity, like we see in silicate melts, which suggests that we might be able to use the oxidation state in apatite as a new petrologic tool. We also confirm Brian's hypotheses that there are sulfur 2- substitutions in apatite, and that it partitions into the column site. Someone asked about this at the beginning, in place for fluorine and chlorine and hydroxyl. This, of course, has important implications if we're going to measure the abundance of hydroxyl in apatites to then calculate the water concentration of magmas on the moon, on Mars, on asteroid bodies. Whether or not there is significant proportions, hundreds or thousands of ppm of sulfur 2- dissolved in that column site will really impact those calculations. And so this will be an important thing to add to our collection of measurements of meteorite materials. And then I'm showing you now the range in the activity of oxygen from Earth. And so this suggests that there are apatites from Earth that have mixed sulfur speciation that have just evaded our observation under the assumption that it's all there as sulfate. And Adam Simon's group is looking at mine tailings and finding these apatites of mixed sulfur speciation. And so that's good. And then I'm also showing you the range in the activity of oxygen for those Martian lavas. Remember that when we looked at the range in the activity of oxygen recorded by the inner solar system bodies, Earth stands out as having this enormous range, and Mars stands out for having a pretty enormous range in the activity of oxygen too, which I'm demonstrating here through this bar, ranges by 5 or 6 orders of magnitude. And it's possible that apatite will help us understand whether there are volcanological processes that are pushing those values to more oxidized or more reduced ends, and to solve, help us understand the formation of those rocks a little better. Along those lines, I have started to measure the oxidation state of sulfur in apatites from a variety of Martian meteorites. And so Nakla meteorite and Lafayette meteorite are both Naklite meteorites. These are basaltic rocks that are erupted to the Martian surface and to some extent appear to interact with the Martian surface, the soils and things that are present there. And then Shergatti is Shergatite, the type Shergatite, which are closer in composition. They're more mafic and potentially more closely related to the Martian mantle. We find that apatites in Shergatti have only sulfur 2-, that they appear to be reduced, and that the Naklites that we've measured so far, Nakla and Lafayette, have apatites that extend the full range from sulfur 2- only to sulfur 6+ only. And so it appears like we can begin to interrogate how volcanological processes change the activity of oxygen of lavas erupted to the Martian surface. And so that's a really exciting direction that we're going in. Just real quick, I'll point out that this is what the Naklite meteorite looks like. It's a highly fractured rock. The apatites are these teeny tiny medium gray grains embedded in the rock. And I'll compare that directly to the Apollo rock and just point out the importance of returned samples in microanalysis, that as we get these focused beams, 2 by 2 microns, even smaller, we're able to interrogate isotopes and oxidation states and abundances of very low abundance elements. It becomes really important that we're looking at thin sections that look more like the sample on the left than the sample on the right, which has been through a minimum of 2 impacts, the one that ejected it from the Martian surface and the one that landed it on the Earth's surface. It becomes important, you see all the fractures in this rock. If there is sulfur that comes from the way that these rocks are stored on Earth that becomes oxidized and embedded in these cracks and pits, it becomes absolutely critical to understand how we avoid that. And to that end, I'll flip through this quickly. To that end, we're going to study Apollo rocks that were recently re-released. So we're going to look at rock 71036. This is an Apollo 17. They've changed the prefix nomenclature again. Apollo 17 rock picked up from this breccia boulder on the lunar surface. And within 2 weeks of its return to Earth's surface, it was in a nitrogen atmosphere, and within a month it was cryogenically frozen, and it was kept that way until 2019 on the 50th anniversary of the Apollo 11 landing on the moon. And so because this rock has not had the ability to just be kicking around in everybody's labs, we're going to get our hands on a thin section of it and measure those apatites and glasses and see if we find any of that oxidized sulfur or not, to try to confirm or refute the terrestrial origin of the mysterious sulfur 6+ signal we see in the lunar rocks. These are my conclusions, and if anyone has time, I'd be happy to answer more questions, but if not, thanks for listening.
Excellent. There are indeed a few questions. I guess I'll start very briefly. If you go back to your figure that had the 4 stacked sulfur spectra with, for example, the apatite in the glass, that one. Yeah. Should I be surprised that the Zanes for the apatite in the glass is so very similar, given that second coordination shell at least could be very different?
That's a good question. I don't know.
Okay, all right. It might be common in mineral melts that it looks very similar, but it jumped out to me. Paul Northrup, you had a question?
Yes, can you hear me?
I can.
I was wondering if you had tried speciation mapping. So mapping of sulfide versus sulfate by making 2 maps at two energies?
No, we haven't tried that for these samples. Most of these are not, yeah, it would be useful to spend, I think, an evening making one of those maps the next time we get to sector 13. Most of these are really dominated by sulfide. And so you can kind of see out of whatever this is, the 40 analyses that we ran on this particular day, there's only a couple that pop out as sulfate. And so it might only pop up as a couple pixels, but who knows? It's a good idea.
Okay.
All right, a question on behalf of Brian Konicki. What are the average compositions of the silicate melts in contact with the apatite, and are they primitive or evolved?
Oh, very evolved. These are really silica potassium rich glass. Really, really evolved. More evolved than your experimental glasses even.
Okay. Liz, do you have your mic working? You had some questions, Liz Cottrell?
I do. Well, I don't know if I was asking a question so much
Liz
as
is my former PhD advisor, just in case anyone didn't know.
but long enough ago that I wasn't aware of this work. So I was more, I think my comment was, wow, that Mars data is amazing. What does it mean? I mean, what's your interpretation of
yeah, I took out a couple of slides here because I thought we might get into more question and answer stuff about the measurements. But these, so if we were to look at, if I go one more slide, now these samples that are bolded are the ones specifically taken in this particular field of interest. There's a sulfide present in this area. There is a glass, right? All of this kind of medium gray stuff is a glass, right? And there are the apatites. The apatites and the glass close to the sulfides are reduced, and the apatites and the glass far away from the sulfides are oxidized. And so there's a process here. And the two options are, it has degassed, and from my biases working on terrestrial rocks, I think this would lead to reduction so that the lava would have started oxidized and been reduced. Or it means because these roll over the Martian surface and the Martian surface, the soils are really sulfur rich, it assimilates those sulfur rich materials. It could have started out reduced and become oxidized. And so we wrote a proposal to NASA to try to do some major element work and more careful, like major element, trace element, volatile work on these thin sections to solve that problem. And so hopefully the mixture, the demonstration that these Martian rocks are recording a really wide range in sulfur oxidation states helps them agree to give us the money necessary to figure out the volcanological problem associated with these measurements.
Okay, well, I hope you'll potentially be willing to give this talk again to I think the planetary and meteorite group at
Smithsonian. Oh, I would love to at the Smithsonian.
Yeah. And maybe Carnegie might do a joint seminar or something, although this is recorded, right? So people can look. And my other question was, what are the prospects for application of this to exhumed terrains, xenoliths, or do we not expect the kind of dynamic, I mean, the dynamic range you're showing with these measurements is just blowing my mind. And I'm just wondering.
Anywhere you expect to find something that lives in the neighborhood of QFM to QFM +2, right? This could record the process. Complicated in that you're talking about metamorphic rocks. And so the relationship, what I've done here is a little bit of a trick because I've measured the sulfur oxidation state of the glass and used the experimental calibrations to say what the FO2 is. And then I measure the sulfur oxidation state of the apatite next to that glass to show you where it falls on the y-axis. And so I'm very much needing like Brian's work and Pedro Hugo's work on the silicate glass for the position on the x-axis. How you're going to do that with metamorphic rocks where it's precipitating from an aqueous fluid, good luck.
Okay, thank you.
Yeah.
All right,
So
last question from Yang Ha.
Hi, great talk.
Thank you.
I realized that you're trying to assign the sulfur species basically based on the edge energy, but it's been pretty generic, like you say, this is a sulfide versus a sulfate. But in some cases, when you have sulfur bound to a transition metal, you might generate a low energy pre-etch. Like at the beginning of the talk, you said you have like 30% of iron in your rocks. And if it's an iron sulfide, you may see a pretty low energy pre-etch feature, and with other transition metals, there's a similar thing. So have you considered that as well in your like data analysis?
Yeah, the bulk planets have 30 weight% of iron in them. Of course, they have very iron-rich cores, which are gigantic. And so the mantles, the silicate mantles of those planets have much lower iron, and the melts they produce, the basaltic melts have more on the order of like 8 to 10 weight% iron in them. And then in particular, these glasses, Brian asked a couple of minutes ago, their composition, they're very, what we were saying in that conversation, evolved. They have very low iron concentrations. Very, very low. So like a weight% or lower in these very evolved liquids that are in connection with the glass. So I think much lower iron concentrations than you might be thinking based off of where I started talking about bulk planet compositions. It's true that what would be great if I had an experimental apatite, maybe Brian can make one, an experimental apatite that contains only sulfur 2- to be using as my end member, my reduced end member spectra in this process. But they don't exist. Thus far, Brian's apatites are very tiny yeah, the sulfide only end member is complicated by the sensitivity of the sulfide peak position to cation identity, for sure. It's a major challenge. Especially as we move forward to try to do stuff like this, where now if we measure the sulfur oxidation state of the apatite, we want to be able to say the activity of oxygen in the rock will require knowing this value on the y-axis very precisely, which right now there's probably like I believe me at like a plus or minus 10%